You might think hitting light speed would make stars smear into long streaks, and the universe blur past like in a movie. But it's almost the reverse. As you push toward that limit, the distance in front of you slams flat. Your own time nearly stalls, while the rest of the universe races ahead, and the quiet night sky doesn't gently stretch. It collapses into a blinding blue-white spear of radiation straight ahead. In modern physics, the speed of light is not just very fast, it is the built-in conversion rate between space and time. It connects meters to seconds in the equations that describe how electricity and magnetism behave. When Einstein wrote down special relativity, he did not treat light speed as a random property of photons, he treated it as a constant of space-time itself. The rule is simple: no information, no physical influence, no cause can travel faster than this speed. If something did, you could create situations where cause and effect swap places, depending on who is watching. One observer could see you send a message, another could see the reply arrive before you sent the original message. In one frame, the cause comes first, in another frame, the effect comes first. That breaks the basic idea that the universe has a consistent history. To avoid that contradiction, the universe enforces a hard limit. The closer you push a massive object toward light speed, the more aggressively its energy, its time, and its lengths fight back. The equations do not gently slow you down, they make the energy cost blow up so that reaching the speed of light for anything with mass would demand infinite energy. This still might sound abstract, like something that only lives in theory. So the next question is direct. Have we ever pushed real matter close enough to light speed to see these effects switch on in a dramatic way? Yes. Particle accelerators do this constantly. In the Large Hadron Collider, we take protons and accelerate them until their speed is 0.999999991 times the speed of light. At that point, writing the decimal fully is almost pointless. The difference between their speed and light speed is incredibly tiny. What matters more is that their Lorentz factor, usually called gamma, is around 7,000. You can think of gamma as a multiplier that tells you how much time, length, and energy are distorted compared to ordinary speeds. From the lab's point of view, those protons move around a ring 27 kilometers long, about 17 miles. From the proton's own frame, the story is extremely different. Along the direction of motion, lengths contract by that factor gamma. Divide 27 kilometers by 7,000 and the effective distance around the ring in the proton's frame shrinks to just a few meters. The proton behaves as if it is racing around a short track again and again, while the outside world thinks it is on a huge loop. Time also changes. The internal clock of a particle, for example as its decay lifetime, stretches by that same factor when you watch it from the lab. Particles that normally fall apart in a tiny fraction of a microsecond can survive long enough to cross the entire detector. If we ignored time dilation and length contraction, the beams in the LHC would not survive long enough to collide and the data would not match predictions. The machines only work because relativity is exactly right at these insane speeds. So at this point you know two things. There is a universal speed limit tied to the structure of space-time, and we have already pushed small pieces of matter close enough to that limit to see space contract and time slow by huge amounts. That brings up the next issue. If space and time change like that when you move fast, what does that do to your basic idea of distance? Take a simple example, the distance to Alpha Centauri, the nearest star system beyond the Sun. In the rest frame of the galaxy, and for people sitting on Earth, it is about 4.3 light years away. A light year is roughly 9.5 trillion kilometers, or about 5.9 trillion miles. If you could somehow move at exactly light speed, someone on Earth would say the trip took 4.3 years. That feels clean and fixed. Now put yourself on a ship that can go very close to light speed, say 99% of it. In that case, your gamma factor is a bit over 7. From Earth's viewpoint, you leave, you travel across 4.3 light years at 0.99 c, and you arrive a little over 4.3 years later. But on board your ship, time is running slower by that factor. Divide 4.3 years by around 7, and the proper time you experience during the cruise is only about 7 or 8 months. At the same time, in your frame, the distance you have to cross is not 4.3 light years. It is that distance divided by the same factor. Instead of about 4.3 light years, the gap in front of you is closer to 0.6 light years. From your point of view, you crossed a shorter distance in less time, without ever feeling anything strange inside the ship. Your watch, your heartbeat, your thoughts all feel normal. But the outside universe insists the journey took years. If you push the speed even closer to light, gamma climbs higher, and this effect gets more extreme. You can, in principle, make trips that look like decades long from Earth's perspective, while you personally age only months or weeks. Distance and duration stop being single, absolute numbers. They become frame-dependent. They depend on how fast you move. So when you ask, what would the universe look like at the speed of light? The strict answer is not about a camera view or a window scene. It is really a question about how space and time behave when you push them to their limit. Light speed is the edge where the normal ideas of distance, duration, and even a sensible viewpoint start to fail. That raises a hard problem. You keep talking about your frame and your clock as you go faster and faster, but light itself does not have mass and never slows down. Do you even get to talk about being with a photon, or is that concept already broken before you start? To answer that, you have to face one of the most uncomfortable facts in relativity. There is no such thing as a rest frame for light, and that changes the whole way you think about seeing the universe at light speed. How do you sit next to something that is never at rest, not even for a split second? That is the first hard wall you hit with light. In special relativity, only things with mass get to have a rest frame, a state where you can say, I'm the one standing still and everything else is moving past me. You, your ship, a planet, a proton, all of those can in some frame be at rest. Photons, the particles of light, are different. They have no rest mass at all, and the only speed they ever have is the speed of light in a vacuum, about 300,000 kilometers per second, roughly 186,000 miles per second. There is no frame where a photon says, I'm stationary. If you try to picture yourself riding along with a beam of light, you're asking for a frame that the equations simply do not allow. This is not just a language trick, it is built into how space-time is structured. When you transform from one moving frame to another, you can always slow a massive object down, at least in principle, to rest. But the same math says no matter what, light keeps that same speed in every inertial frame. The transformation you would need to slow it to zero is not physically allowed. So the phrase, what does the universe look like to a photon, is not a deep secret insight, it is a broken question. It is like asking what is the colour of 10 kilograms, or what is the temperature of the direction left. The concept you are trying to use just does not apply. That sounds very unsatisfying, so the next question is, if you cannot sit on a photon, is there still a meaningful way to talk about what happens as you push your own speed closer and closer to that limit? The trick is to stop at almost, and study how time behaves as you approach light speed without ever reaching it. Physicists wrap all of the relativistic effects into one number, called the Lorentz factor, or just gamma. Gamma tells you how much your time slows down, and how much lengths along your direction of motion shrink, compared to someone who is not moving with you. Gamma is always at least 1. When your speed is small compared to light, gamma is basically 1.0 something, so the effects are tiny. As your speed v gets close to c, gamma climbs. The way you calculate it in words is, you take 1, you subtract the square of your speed divided by the square of light speed, you take the square root of that whole thing, then you take 1 divided by that number is gamma. At 90% of light speed, around 270,000 kilometers per second or 167,000 miles per second, gamma is about 2.3. That means your clock, the one you carry, runs more than 2 times slower than a clock back on Earth. At 99% of light speed, gamma jumps to about 7, so your 1 second matches about 7 seconds for people who stayed behind. At 99.99% of light speed, gamma is around 70, so 1 second for you lines up with more than a minute on Earth. These are not just abstract numbers written on the board. The next question has to be, do we actually see this time stretching in real experiments, Or is it just a neat story? Particle accelerators give a very direct answer. Take the muon, a heavier cousin of the electron. When a muon is at rest, it survives on average about 2.2 microseconds before it decays. That is 2.2 millionths of a second. Not much time. In a storage ring, we accelerate muons to speeds like 0.9994 times the speed of light. At that speed, gamma is about 30. Suddenly, those same muons, watched from the lab, live roughly 30 times longer. Instead of 2.2 microseconds, they hang around for more like 60 or 70 microseconds. If that extra lifetime was not real, if their internal clocks were not slowed by their motion, we would see almost none of them make it around the ring. The beam would vanish too quickly, the detectors would stay mostly quiet, the whole design would fail. Instead, the data matches the relativistic prediction extremely well. Push protons in the Large Hadron Collider to their top energies, with speeds of 0.999999991 C, and gamma is not 30 anymore, it is around 7,000. Any unstable particle created in those collisions, with some natural lifetime when at rest, now appears to live thousands of times longer, as seen in the lab. Those stretched lifetimes are part of how we identify particles and measure their properties. So the machines we build on Earth only make sense if time dilation and length contraction are real. That leads to another, even more serious test. Does nature herself, outside the lab, also use this same relativistic rulebook? Cosmic rays answer that. High-energy particles from space slam into the upper atmosphere at altitudes of around 10 to 15 kilometers, 6 to 9 miles up. These collisions create showers of secondary particles, including muons. Remember, at rest, a muon's lifetime is about 2.2 microseconds. Even at light speed in 2.2 microseconds, you would only travel about 660 meters, around 2,200 feet. The ground is much farther away than that, so if their clocks ticked at the normal rate, almost all of these muons would decay high above you. But detectors at sea level see a lot of muons, far more than you would get without relativity. The only way to make the numbers work is to accept that from our frame, the muon's internal clock is running slower because they are moving at more than 98% of light speed. With that slower clock, they can live long enough in our time to reach the ground. Flip the viewpoint. From the muon's own frame, its lifetime is still just 2.2 microseconds. That does not change. What changes instead is the thickness of the atmosphere. Along its path, that 10 or 15 kilometer layer is length contracted down to something like a few hundred meters. In its reality, it does not need extra time because there is less distance to cross. Both stories are correct, each in its own frame, and both match the measurements. So you now have lab beams and cosmic particles all following one rule: the closer you get to light speed, the more time and space twist for you. That raises the key question that this whole topic is pushing you toward. If time slows and distances shrink as you approach light speed, what happens if you try to go all the way, right to the limit? Here is the precise but uncomfortable answer. For light itself, the idea of a ticking clock along its path simply does not exist. In relativity, you can talk about the proper time along a path, meaning the time experienced by something travelling along that path. For anything with mass, between two events, that proper time is always a positive amount. For a light path, the proper time is exactly 0. That means, between emission and absorption, there is no passage of time in the sense that you and I understand it, for a photon. There is no series of moments, no before and after, no changing view. There is just one null path in space-time with 0 proper time between its endpoints. When you ask, what does the universe look like at the speed of light, the strict answer is, for light, there is no sequence of looks at all. So to make the question meaningful, you have to rephrase it. You do not ride on a photon, you ride a ship as close to light speed as engineering and physics allow, you accept that your time slows, and you ask, what do you actually see? And how does the universe behave around you in that extreme limit? And once you do that, another, even sharper question appears. How close to light speed do you actually have to go before normal ideas of time and distance just stop working? You might think you need to hit 100% of light speed to see anything dramatic. You don't. You only have to push one number, the Lorentz factor, gamma, high enough, and reality already starts bending hard. Gamma is your relativity dial. At walking speeds, gamma is basically 1.00000000, so nothing weird happens. At highway speeds, same story. But as your speed climbs, gamma creeps up, and every tiny increase hits you in 3 ways at once. Your own time runs slower, lengths in front of you shrink, and the energy you need to go even a little faster explodes. At 90% of light speed, about 270,000 kilometers per second, roughly 167,000 miles per second, gamma is about 2.3. That means, compared to someone at rest, your clock is running a bit less than half as fast, and distances in your direction of travel are a bit less than half as long. At 99% of light speed, gamma jumps to about 7.1. Now your 1 second lines up with over 7 seconds for people you left behind, and the distance in front of you is shrunk by that same factor, more than 7 times. Pushed to 99.9% of light speed, gamma is around 22. Your time is crawling compared to the outside universe, and the space in front of you is crushed to about 1/22nd of its normal length. By 99.999% of light speed, gamma is over 220. Now any further increase in speed costs a stupid amount of energy. Doubling your speed in a car is easy, a bit more fuel, a bit more throttle. Near light speed, nudging that last tiny fraction, adding even a 10,000th of light speed, can cost more energy than an entire modern country uses in a year. So the first shock is this. You don't have to hit the full speed of light to wreck your intuition. Once gamma gets big, the universe is already playing by a different rule book. That leads straight to the next question. When your gamma is high, what actually happens to the distances you care about? The gaps between stars, the length of your journey? Take a clear, simple setup. In the rest frame of the galaxy, there is a star 10 light years away. That means light moving at full speed needs 10 years to get there. For people sitting on Earth, watching your ship leave and arrive, that distance is fixed at 10 light years. If your ship cruises at 99% of light speed, they see you take a little over 10 years to reach it, because you're just slightly slower than light. Now switch to your frame on the ship. Your speed is still 99% of light speed, but your gamma is about 7.1. That number hits the distance straight on. In your frame, the gap between you and that star along your direction of travel is not 10 light years anymore. You divide that by gamma. 10 divided by about 7 gives roughly 1.4 light years. So from your point of view, the star is only 1.4 light years away. You travel at 0.99 c across 1.4 light years, so the trip, according to your own clock, takes about 1.4 years. You eat meals, you sleep, you fix things on the ship. About a year and a half passes for you and you arrive. People back home in the galaxy's rest frame insist the journey took a little over 10 years. Both stories are right, because distance along your path is not a universal number anymore. It depends on your motion. At high speed, the universe in front of you literally flattens. Once distance can shrink like that, you immediately have to ask, what about time on everyone else's clocks? Whose clock is really slow? From Earth, the answer is simple. Your ship's clock is slow. They watch your signals, count your heartbeats, measure the ticking of your onboard instruments, and they see everything on your ship running behind their own time by that factor gamma. At 0.99 c, they say, your seconds are stretched, your chemistry is slower, your aging is slower, everything about you is in slow motion compared to them. From your seat, on the other hand, your own body and your own clock feel completely normal. You do not feel slow. Instead, when you look back at Earth, you see their clocks as the ones that are dragging. Their seconds are long, their processes are slow. That's the key point. Each inertial frame sees the other one's clock as slow, while the relative speed stays constant. At 0.99 c, every second on your ship can match more than 7 seconds back home. At 99.99% of light speed, gamma is around 70, so a single day for you can line up with a couple of months on Earth. This is not just a thought experiment. We already have to correct for relativity at much lower speeds, or our tech breaks. GPS satellites, for example, orbit at about 3.9 kilometers per second, around 8,700 miles per hour. At that speed, their clocks tick a few microseconds differently per day compared to clocks on the ground, from both special relativity and gravity. If engineers did not build those shifts into the system, your phone's position would drift by kilometers. So even at a few kilometers per second, we see time becoming frame dependent. At 0.99 C and beyond, it becomes violently frame dependent. That sets up a very practical question. If you actually tried to go to a real target like Alpha Centauri with these speeds, how different would the story of the trip be for you versus for Earth? Alpha Centauri is about 4.37 light-years away, roughly 4.1 times 10 to the 13th kilometers, which is around 25 trillion miles. In the rest frame of the stars, that's the distance. If your ship can cruise at 0.99 C once you're up to speed, someone on Earth sees the trip take about 4.4 years of their time from departure to arrival, a bit more than the raw distance in light-years because you're not at exactly C. On board though, with gamma a bit over 7, you divide that 4.4 years by gamma. That gives you around 0.6 years, so about 7 to 8 months of your proper time, that's including the coast phase at top speed. Depending on how you handle acceleration and braking, the exact number changes, but the main point holds: you can personally experience a trip to the nearest star system in under a year, while everyone watching from home waits more than 4 years. Push the cruise speed even higher, say to 99.99% of light speed. Now gamma is around 70. The distance to Alpha Centauri in your frame shrinks by that factor. The proper travel time you feel drops to just a few weeks. For you in the ship, nearby stars start to behave more like long-distance flights than multi-year voyages. For the outside universe, the trip is still years long. So mathematically, with high gamma, interstellar trips can fit into human-scale lifetimes, at least for the travellers. But something feels wrong to your intuition here. Your head keeps screaming that you can't just cheat distance and time like this. If both sides are right in their own frame, what is your brain missing? The problem is simple. Your brain was never asked to deal with these conditions. Human intuition grew up in a world where gamma is basically 1, all the time. At car speeds, at plane speeds, even at old Apollo speeds, gamma differs from 1 by such a tiny fraction that it might as well be 0. At 30 meters per second, around 70 miles per hour, gamma is 1 plus a correction of about 15 decimal places down. At 8 kilometers per second, low Earth orbit speed, gamma still differs from 1 by only a few parts in a billion. In that regime, Newtonian physics is an amazing approximation. Time feels absolute, distance feels absolute, adding and subtracting speeds is straightforward, and everyone's now is basically the same. Your nervous system has no reason to develop a sense for how space-time behaves when gamma is 7 or 70 or 700. So as soon as you enter that high gamma world, everything you thought was solid, length, time, energy, mass starts to get renegotiated. And here is the real cliffhanger. All of this so far has only talked about how clocks and rulers behave. You have not even touched what it actually looks like out the window when you race through the galaxy at 0.99 C, how the star field itself changes. When your speed climbs that high, light does not just shift colour, it changes direction in your frame, and the whole sky starts to collapse into a bright, distorted tunnel in front of you. To see how that happens, and why almost the entire universe seems to get squeezed into your forward view, you have to look at how motion at near light speed literally bends the directions that starlight comes from. How does the sky react when you stop crawling and start moving at a real fraction of light speed? You might expect the stars to just streak sideways, like car lights in a long exposure photo. That's wrong. At near light speed, the universe doesn't slide past your side windows, it collapses into the space directly in front of you. This happens because motion doesn't just change how fast light arrives, it changes the direction it seems to come from. That effect is called aberration of light. In your normal life, it's so small you never notice it, but it's already there. Even right now, Earth is orbiting the Sun at about 30 kilometers per second, roughly 67,000 miles per hour. That's only about 1/10,000th of light speed, so V over C is around 0.0001. At that tiny fraction, astronomers still measure that stars appear slightly shifted from their true positions by about 20 arcseconds. That is a tiny angle, about 1/180,000th of a degree. But it's real, and it repeats every year as Earth's direction of motion changes. The reason is straightforward. You're moving sideways while the light from the star is coming in. To keep that beam of light entering a telescope, you have to tilt the telescope slightly into the direction you're moving, like holding an umbrella into the rain while you're walking. The rain seems to come from ahead of you, even if it's falling straight down. With starlight, that tilt is the aberration angle. At Earth's orbital speed, it's small, but the key point is, the effect is already there at V over C of 0.0001. Near light speed, the same geometry takes over your entire field of view, so this isn't a new, untested idea. Aberration has been measured for centuries. Back in 1728, the astronomer James Bradley was trying to measure stellar parallax, the tiny shift in star positions as Earth orbits the Sun. Instead, he noticed a different pattern. The apparent positions of stars were tracing out little ellipses over the course of a year, but not in the way parallax predicted. The only explanation that fit was this: Earth is moving around the Sun, light from stars travels extremely fast but not infinitely fast, and our motion tilts the incoming light in our frame. Bradley had basically measured the vector sum of Earth's velocity and the light's velocity. From that data, he could even estimate the ratio of Earth's orbital speed to the speed of light. That was with V over C of about 0.0001, and yet the effect was clear enough with 18th century telescopes. Now take that same effect and give your ship a velocity of 0.9 c or 0.99 c. You're repeating Bradley's experiment, but with speeds almost 1,000 times larger. At that point, aberration doesn't just nudge star positions, it dominates everything you see. So what does the sky actually look like once your ship is up to, say, 90% of light speed? From the galaxy's rest frame, stars are spread almost evenly across the whole sky. Some are ahead of you, some behind, many off to the side. From your moving frame at 0.9 c, though, the directions of incoming light are transformed. Light that in the rest frame was coming from the side or even from behind you now appears shifted toward the front. As your speed increases, the angles of those rays in your frame get squeezed closer and closer to your forward direction. At 0.9 c, a large fraction of the star field that used to be off to your left and right is now visible somewhere in a wide cone in front of you. Push to 0.99 c, and it gets extreme. The math says, when your speed is very close to light speed, almost any light that is not exactly dead behind you will appear to come from within a small forward cone. In words, as V approaches C, the transformed angle between your velocity direction and the incoming light shrinks towards zero for almost everything. The back half of the universe, from your point of view, is getting wrapped around into the front. So your view stops being a calm all-sky dome. It turns into something like a relativistic tunnel, where almost every external object appears somewhere ahead. Not because space itself is turning into a tunnel, but because the paths that photons take in your moving frame are being squeezed into that limited range of angles. Behind you, the sky empties out. In front, it gets more and more crowded. Position is only half the story. Aberration tells you where things appear. The next problem is how bright they look. Once again, near light speed does something your everyday experience never prepared you for. When you move fast through a field of light sources, that light isn't just redirected, it gets concentrated forward. This is called relativistic beaming, or sometimes the headlight effect. In the rest frame of a star or a galaxy, it sends out light more or less evenly in all directions, but in your frame, if you are moving toward it at a large fraction of light speed, most of the photons it emits that actually reach you are ones that in your frame come from a narrow forward cone, so not only does aberration drag star positions toward the front, beaming also stacks their light into that same region. The intensity you see from sources in front of you increases, and the intensity from sources behind you drops. Ahead of you, the sky grows not just more crowded, but far brighter and more concentrated. Behind you, things fade into a dim, almost empty glow. Astrophysicists see this effect on a huge scale with jets from active galactic nuclei and pulsars. When a jet is aimed close to our line of sight, the radiation from particles in that jet, which in their own frame is fairly spread out, becomes focused into a narrow beam in our frame. Those jets can then look absurdly bright, sometimes so bright they outshine the rest of their galaxy. We call some of those objects blazers. Your near-light speed ship would put you in a similar situation, except now the beamed light is the entire forward universe. Now stack everything together. You have high gamma from your speed, which shrinks lengths along your path. You have aberration, which hauls the apparent positions of stars and galaxies into a forward cone. You have beaming, which boosts the brightness in that same cone and drains light from behind you. From your perspective on the ship, the universe is no longer a calm, symmetric sphere around you. It looks reoriented around your motion. Forward is no longer just one direction, it becomes the preferred direction, the place where almost everything now lives visually. Sideways and backward fade into irrelevance. At everyday speeds, these effects are too small to see. At 0.9 C or 0.99 C, they are the main thing you see. So far, this is all about where photons are coming from and how many of them hit you. But each photon carries energy, which means it has a colour, a wavelength. When you push to near light speed, you don't just bend the sky into a cone, and you also brutally shift those colours. The light in front of you gets squeezed into higher and higher energies, while the light behind you gets stretched into lower energies until it practically vanishes. That is where the next step gets dangerous, because at high enough speed, ordinary starlight in front of you stops being harmless and starts turning into ultraviolet, X-rays, even gamma rays. To see how that happens and how your near light speed ship turns the entire universe into a giant radiation machine, you have to look at the relativistic Doppler effect and watch the colours of the cosmos go completely out of control. What happens when the sky in front of you doesn't just get crowded, but starts changing colour so violently that normal starlight turns into hard radiation? Once your speed gets close to light, that's exactly what happens, because of the relativistic Doppler effect. When you move toward a source of light, the waves you're running into get squeezed together in time. The peaks of the wave hit you more often, so the frequency goes up and the wavelength goes down. That shift to shorter wavelengths and higher frequencies is called blue shift. Move away from a source and the opposite happens. The peaks are more spread out, the frequency drops, the wavelength stretches, and you get red shift. At low speeds, this Doppler effect is mild. You see it with sound all the time. Sirens pitch up when they move toward you, then pitch down as they pass. For light at car speeds, the shift is microscopic. But at relativistic speeds, the normal classroom Doppler formula is not enough. You have to use the full relativistic one, which takes time dilation into account. If you plug 99% of light speed into that relativistic formula, the factor that tells you how much the frequency changes for light coming straight at you is about 14. That means, in your forward direction, every incoming photon's frequency is multiplied by roughly 14, and its wavelength is divided by the same factor. A typical green photon from a star like the Sun might peak around 550 nanometers. That's in the middle of the visible spectrum. Divide that by 14 and you're down around 40 nanometers, which is deep in the ultraviolet, bordering on soft X-rays. So at 0.99 C, a star that would look comfortable greenish white to someone at rest now throws UV and soft X-ray photons at your forward windows. The colour shift is not cosmetic anymore. It's biological and technological. It can burn and ionize. That leads straight into the next question. If you push faster, does ordinary starlight actually become dangerous X-rays and gamma rays? take a sun-like star again. To someone sitting still relative to it, most of its energy comes out in visible light and near infrared, so wavelengths from a few hundred to a few thousand nanometers, with photon energies of a few electron volts. That's what your eyes and skin evolved under. Now put your ship at 99.9% of light speed, so 0.999 c. In that case, the relativistic Doppler factor for light you are flying straight into can climb toward 20 or 30 depending on exact direction, and if you go even closer, 0.9999 c, it can be tens to hundreds. Multiply the photon energies by those factors. A 2 electron volt visible photon pushed up by a factor of 100 becomes a 200 electron volt photon, firmly in the X-ray range. Push harder, and you get into thousands of electron volts, or kilo electron volts, the kind of energies used in medical CT scanners. So your forward sky, which in the rest frame of the galaxy is a mix of visible and infrared starlight, becomes, in your frame, a fog of far ultraviolet and X-rays. This is not light you look at with sunglasses. This is light that rips electrons off atoms, damages DNA, and slams into electronics. You are flying into a radiation storm created by your own motion. You would need serious shielding, meters of dense material or advanced magnetic fields just to keep the crew alive. You can think of it this way: at relativistic speeds, you are not just moving through the universe, you are converting harmless background light into a high-energy weapon pointed straight at your bow. So is this just a weird trick of going fast? Or does the universe already do the same thing on large scales? The same physics runs the show in cosmology. When galaxies move away from us because space itself is expanding, the light they send out arrives with longer wavelengths than when it left. Spectral lines from hydrogen that should sit in the visible part of the spectrum get dragged into the infrared, then into microwaves, then into radio for the most distant galaxies. That is cosmological redshift, the stretching of light by the expansion of space over billions of years. The cosmic microwave background is another example. Right after the Big Bang, this radiation was more like a hot, ultraviolet and visible light bath. As the universe expanded by a factor of about 1,000 in linear size, the wavelengths of those photons were stretched by the same factor. What was once searing UV is now microwave radiation peaking at around 2.7 Kelvin, with wavelengths of about 2 millimeters. Your relativistic ship can recreate that kind of shift in a single moment, simply by changing your velocity. The universe uses billions of years of expansion to stretch light. You use a near light speed boost to either stretch or squeeze it. The mechanism changing the relationship between emitter and observer is the same. But you might still ask, do we really see such extreme blue shifts and red shifts in real objects at speeds close to what we're talking about for this ship? Or is this still mostly theory? Quasars answer that. These are active galactic nuclei where a supermassive black hole sits in the center of a galaxy and launches jets of plasma at speeds of 90% of light speed or more. When astronomers break their light into spectra, they find emission lines shifted by amounts that match bulk velocities of 0.9 c and higher in those jets. In X-ray binary systems, where a normal star orbits a compact object like a neutron star or a black hole, gas in the inner disk can orbit at tens of percent of light speed. X-ray telescopes see ion emission lines from that gas that are broadened and skewed exactly in the way relativistic Doppler and gravitational redshift predict. Parts of the disk moving toward us are blue shifted, parts moving away are redshifted, and the whole profile shows that light is being battered by both high speed and strong gravity, so the spectral gymnastics you expect from relativity are not hypothetical. Radio telescopes, optical telescopes, X-ray and gamma-ray observatories all record these shifts. Nature already runs near light speed experiments all over the sky. Now put yourself back on the ship. You're not just a passive observer of these Doppler shifts, you become a source of them. Your motion through the interstellar medium turns even tiny particles and faint radiation fields into high-energy hazards. Consider a dust grain with a mass of about 10 to the minus 12 kilograms. That's a trillionth of a kilogram, lighter than a speck of sand, hitting your ship head-on at 0.9 c. The kinetic energy of that grain is roughly 1/2 times its mass times its speed squared. Plug in 0.9 times 300,000 kilometers per second, and you get an energy on the order of 10,000 joules. That's similar to the chemical energy released by detonating a few grams of TNT, delivered into an impact site smaller than a pinhead in a time less than a billionth of a second. Each of those impacts can vaporize a bit of your hull, generate a flash of X-rays and gamma rays, and spray secondary particles into your ship. At 0.1 c, this is already a problem. At 0.9 c and beyond, it becomes one of the main engineering nightmares. You have to treat interstellar space, which at normal speeds feels empty, as a dense, dangerous radiation environment, because your own motion is cranking up the energy of everything you hit. So near light speed doesn't just bend where light comes from, it hijacks its colour and energy, and it turns gentle starlight and microscopic dust into a constant barrage of hard radiation and explosive impacts. Up to now, though, we've still quietly assumed that everyone agrees on the order of events, that before and after mean the same thing for you and for people back home. At everyday speeds, that's safe, but at 0.99 c, even the idea of what is happening at the same time in different places starts to fall apart. When you push close to light speed, simultaneity itself of full breaks. Your now and someone else's now can be years or centuries apart, and that twist in time is what we have to face next. You're used to thinking that now is a simple thing. Right now is right now for you, for your friend, for the moon, for a galaxy far away. At walking speeds and plane speeds, that feels obviously true, but near light speed, that picture breaks. Even the idea of at the same time stops being something everyone can agree on. Start with something simple. You stand on Earth with a friend some distance away. 2 lightning bolts hit 2 trees, one near you, one near your friend. You both see the flashes you can run over later, compare notes and agree those strikes happened at the same time or they didn't. For everyday distances and low speeds, the delays from light, travel and motion are tiny, so it's easy to clean that up and define a common simultaneous for both of you. Now swap in your near light speed ship. Someone on Earth sets off 2 bright flashes on opposite sides of the planet, timed so that in Earth's rest frame they are perfectly simultaneous. Earth observers place detectors correct for light travel time, and they all agree yes, those 2 events have the same time coordinate. From your ship's frame racing past at 0.99 c, that same pair of flashes does not line up that way. When you work through the relativity math in words, you find this. If 2 events are simultaneous in one frame, and they are separated in space, then in another frame moving relative to the first one, those events will not be simultaneous. One happens earlier, one happens later. Which one is first depends on how you're moving. So your picture of the universe sliced into nows is not the same as Earth's picture. Their line of simultaneity, the set of events they label as happening at the same time, is not the same as yours. Time dilation gets most of the attention because clocks running slow feels concrete. But relativity of simultaneity is at least as important because it wrecks the idea of one global present moment. You already live with the consequences of this without thinking about it because our navigation systems have to take it into account. That's where GPS comes in. GPS satellites orbit Earth at about 3.9 kilometers per second, roughly 8,700 miles per hour, and they sit higher up in Earth's gravity field than you do on the ground. Both of those facts matter. Special relativity says because they're moving, their onboard clocks should tick slower than clocks on Earth by about 7 microseconds per day. General relativity says because they're higher in the gravitational well, their clocks should tick faster than ground clocks by about 45 microseconds per day. Add those together, and a raw GPS satellite clock would get ahead of an Earth clock by about 38 microseconds every day. That sounds tiny, but light travels about 11 kilometers, around 7 miles in 38 microseconds. If you ignored that mismatch, the now that the satellites in your phone think they share would drift. Your reported position would slide by kilometers per day. Engineers fix this by pre-offsetting the satellite clock so that, once in orbit, their tick rate matches the ground frame. In other words, the system is built with relativity baked in. Even at a few kilometers per second, the relationship between their time and our time is not trivial. At 0.99c, it is not just a correction, it is a total rewrite of what now means for you versus for Earth. So what happens when you stretch this difference out over a whole journey, years long, close to light speed? That's where the classic twin paradox comes from. Set up two twins, one stays on Earth, one gets on a starship. The ship accelerates up to 0.99c, cruises for a while, turns around and comes back again at 0.99c, then slows down to land. For the travelling twin, maybe the whole trip, including acceleration phases, takes, say, 10 years of their own proper time. They age 10 years. On Earth, because of their relative speed, clocks see the traveller's time as running slow by about a factor of 7 when the ship is at cruise. When you work through the whole path, taking into account the outbound leg, the turnaround and the inbound leg, you end up with the stay-at-home twin aging much more. Depending on the distances and timing you choose, that could be 30, 40, 50 years or more. The traveller comes back younger than their sibling. Where does simultaneity come in? During each straight, constant speed leg, both twins see the other twin's clock as running slow. That sounds symmetric, so why doesn't it cancel out? The key is the turnaround. The travelling twin changes velocity, which means they switch from one inertial frame to another. When they tipple, the slice of distant events they call now on Earth jumps. On a spacetime diagram, their plane of simultaneity tilts one way on the outbound leg, then tilts the other way on the inbound leg. That jump lines up with a big chunk of extra time passing on Earth, all at once from the traveller's perspective. So this is not just time running slow in a simple global way, it's your whole definition of which distant events are in your present that shifts depending on your motion. That's why the paradox is only a paradox if you ignore simultaneity. Once you track how now tilts between frames, the math and the story match perfectly. As you push your speed closer to light, this tilt becomes extreme. In special relativity, you can picture space-time as a grid. For someone at rest on Earth, time runs straight up the page, space runs horizontally. Their now at some moment is a horizontal line across that grid. For you, sprinting at 0.99c, your time axis tilts relative to Earth's, and your now line tilts too. At modest speeds, the tilt is tiny, you can ignore it. At 0.99c, it's big. At 0.9999c, it's huge. That means, when you leave Earth, you and Mission Control can agree on which distant galaxy events are happening right now. After years of high-speed travel, when you ask again, what is going on right now in that same galaxy, your answer and Earth's answer do not match. For you, that galaxy might already be millions of years further along its evolution than Earth would say, or millions of years behind, depending on the direction you've been moving. So your personal present, your private slice of the universe, depends on your velocity. There is no single observer-independent list of events happening right now everywhere. At low speeds, the differences are so tiny that Newton's idea of a universal clock works well enough. At near light speed, those differences grow so huge that your now and someone else's now can be separated by centuries or more for distant objects. Push all the way to the limit and things go even stranger. For a photon, the interval of proper time along its path is 0. There is no world line with a sequence of moments you can meaningfully call before and after on the photon's own clock, because it has no such clock. That's another way of saying, in the light-like limit, the concept of a plane of simultaneity for that observer just collapses. There is no series of nows to stack up. So when you ask, what do I see at light speed, you are quietly mixing up two things, what your eyes would register, and what you even mean by a present moment when your motion is that extreme. Near light speed, vision, time dilation, and simultaneity all twist together. For actual light, the idea of a flowing time with changing views vanishes. For you with mass, you never reach that limit, but you can get close enough that the rest of the universe's timeline races ahead of yours. Your ship clock stays calm, your biology ticks normally, but out there, galaxies, stars, and black holes burn through their histories in what for you feels like fast forward. So the next step is to stop thinking only about how your clock compares to a clock on Earth, and start tracking how much external time you can burn through by holding a huge gamma for long stretches. If your 1 year can match 100 years out there, or 1,000, then your high-speed voyage doesn't just move you in space, it moves you deep into the universe's future. And when that happens, the cosmos around you stops looking static and starts looking like a time-lapse. Galaxies spinning, stars forming and dying, black holes feeding and quieting, all packed into a slice of your lifetime. To see how extreme that can get, and how near light-speed travel turns the universe into a fast-forward movie for you, we have to look at what happens when you stay at high gamma for months or years of your own time. How much of the universe's future could go by while you only live through a single year? Not in a poetic sense, but in raw numbers on clocks. Once your speed gets extreme and gamma gets huge, the answer is a lot. On your relativistic ship, your own clock always feels normal. Your heartbeat is normal, your 1 second feels like a second, your 1 hour feels like an hour. But you already know that when gamma is large, external clocks are not keeping the same pace. If your gamma is 100, every hour of your proper time lines up with about 100 hours in the rest frame you left behind. 1 hour for you, a little over 4 days elsewhere. Stretch that out. At gamma 100, one of your days is about 100 days outside more than 3 months. One of your months is about 100 months, over 8 years. Keep a cruise like that going for, say, 3 months of your own time, roughly 2,000 hours, and the outside universe has advanced about 200,000 hours over 20 years. Hold gamma at 1,000 and the ratios get brutal. Every day for you is almost 3 years outside. Every year for you is close to 1,000 years of external time. A few months at that gamma would be skipping centuries. So high gamma travel is not just, I get there faster. It is, I move into the future of everything else, while my own body barely ages. That immediately raises the next question. On these scales, could you literally watch galaxies change shape in what to you feels like minutes or hours? Take a standard spiral galaxy like the Milky Way. It makes one full rotation in roughly 200 to 250 million years. From Earth's slow frame, that is unimaginably long. We will never see a full spin, we only infer it from motions. But in principle, nothing stops you from comparing that timescale to your gamma. Suppose, very hypothetically, you could maintain an effective gamma of 10 million relative to the galaxy's rest frame. That is way beyond anything we can engineer, but the math doesn't care. At gamma, 10 million, 1 second for you lines up with about 10 million seconds in the galaxy frame, which is a bit over 115 days. 1 hour for you is over 13,000 years outside. 1 day for you is more than 300,000 years. Now stack those days. A year of your proper time at gamma 10 million corresponds to around 10 million years of galactic time. Hold that for 20 to 25 of your years, and the galaxy has had time to rotate roughly once. Star-forming regions have orbited the center, spiral arms have sheared and twisted, gas clouds have collapsed and lit up. From your point of view, you could compress an entire galactic rotation into a working lifetime. The glowing bands of stars in a spiral arm would not be fixed scenery. They would drift and morph in a slow but visible way, a real time-lapse of galactic evolution. Realistically, you're not getting gamma 10 million with any human-built ship. Propulsion, fuel, shielding, all of that will stop you far earlier. But the point stands, the higher gamma goes, the more the universe's long timescales shrink into something the human brain can directly witness. Processes that normally take tens or hundreds of millions of years can, in principle, slide into your observational window. Galaxies are the slow end. On shorter cosmic timescales, black holes and their disks are already flickering on human time. Accretion disks around stellar mass black holes can change their brightness in hours to days. Active galactic nuclei powered by supermassive black holes can flare or fade on timescales of days to years. X-ray telescopes routinely watch the X-ray output from these objects double, then drop within a single observing run. Now bring gamma back in. If you could cruise at a gamma of 100 near one of these systems, then every hour you experience corresponds to about 100 hours, a little over 4 days in the black hole's frame. A few days of shipboard time would let you see weeks or months of accretion disk changes. At gamma 1000, the effect is even more pronounced. Your one-day match is almost 3 years outside. A project that takes you 10 or 20 years of your own life could let you watch hundreds or thousands of years of black hole feeding cycles. Entire episodes of a quasar turning on, spraying jets, then dimming, which might take 1 million years in the host galaxy's time, could be squeezed into a window small enough to study within a single extended mission, if the geometry and speeds lined up. So near light speed travel doesn't just move you from point A to point B, it lets you run nature's processes in fast forward, not by changing them, but by changing your relationship to time. You turn into a witness of deep time events on a personal schedule, but that cuts both ways. If you can move forward through everyone else's time that fast, what happens when you actually go home? The numbers there are not comforting. Picture this, you leave Earth on a near light speed journey. You accelerate up to some huge gamma, you coast for a while, you explore, you run experiments, then you turn around and come back, keeping similar speeds. Total proper time for you from launch to landing, maybe 10 years. Not crazy for a career mission. During those same 10 years for you, the outside universe has been racing. If your average gamma over the trip is say 100, then those 10 years on the ship align with about 1,000 years on Earth. If your gamma is 1,000, they align with about 10,000 years. Those are not science fiction numbers. That is just multiplying. Come home after 10 years of your life, and you could be stepping out into an Earth that is 1,000 or 10,000 years older. Languages have shifted or disappeared, cities have moved or collapsed, coastlines have changed. The entire technological base is unrecognizable. From a purely relativistic standpoint, that's allowed. You didn't jump in time, you just lived slower than everyone else. Push the scale up. Instead of 10 years of ship time, take 30 or 40. With gamma in the thousands, that aligns us with tens of thousands of years outside. Civilizations, species, even climates can change in that window. Deep time stops being an abstract line on a chart and becomes something you've literally crossed with your own body. And it's not just human history. The sun itself will have burned through a noticeable extra chunk of its fuel. Right now, it fuses about 600 million tons of hydrogen into helium every second. That's 600 billion kilograms per second, or about 660 billion tons per second in imperial terms. Over 1 billion years, that adds up. But even over a few million years, the core composition shifts measurably. After thousands or tens of thousands of years, the change is small, but not zero. After millions, it's significant. The constellations in the night sky will not match what you remember. Stars have their own proper motions, drifting at tens of kilometers per second across the galaxy. Over a few thousand years, their positions shift by enough that familiar patterns start to warp. Over millions of years, the constellations you know now vanish completely, replaced by different groupings. You left behind one sky, you return under another. So near light speed travel is not just crossing space, it is editing your personal connection to time. You choose to sacrifice your link to your own era in exchange for crossing distances and watching cosmic changes that would otherwise be frozen across hundreds of generations. So far, all of this time-lapse effect has been about stars, galaxies, and black holes, which are bright and obvious. But the universe is also filled with something much quieter, a cold bath of low-energy light left over from the Big Bang, the cosmic microwave background. Right now, that background looks harmless and static. At near light speed, it does not stay that way. When you crank your velocity toward light speed, That calm 2.7 Kelvin microwave glow in all directions starts to heat up and pile forward until the entire sky itself turns into a high-energy headwind. To see how chasing light speed rewrites even the afterglow of the Big Bang, we have to look at what happens to the cosmic microwave background when you blast through it at relativistic speeds. There is a radiation field filling all of space right now, so what happens when you slam through it at near light speed? This is not starlight, not galaxies, but the background glow of the universe itself, and at high speed it stops being harmless and starts becoming a real threat. Today, everywhere you go in the universe, there is a faint bath of microwave radiation at about 2.725 Kelvin, just a few degrees above absolute zero. This is the cosmic microwave background, the cooled down echo of the Big Bang. If you could see microwaves, the whole sky would glow almost perfectly evenly, with a characteristic spectrum that peaks at a wavelength of around 1.9 millimeters, a bit under 1/10 of an inch. In your living room, this is just part of the static in radio receivers. It sits buried under local signals and noise, but to a sensitive detector in space pointed at the sky, it shows up as an almost perfect black body curve. This is one of the cleanest signals we have in cosmology, a direct snapshot of the universe when it was only a few 100,000 years old. So at rest with respect to this background, space is cold, uniform and quiet. But you already know from relativity that being at rest is not an absolute thing. It depends on how you move. That leads straight to the next question. How fast are you and the solar system actually moving through this cosmic glow right now? Earth, the Sun, and the whole solar system are not sitting still in the frame of the CMB. Measurements with satellites like COBE, UMAP and Planck show a clear dipole pattern in the microwave sky. One side looks slightly hotter, the opposite side slightly cooler. The simplest explanation is motion. We are moving toward the hot direction and away from the cold one. From that signal, we infer that the solar system is travelling at about 370 kilometers per second relative to the CMB, that's around 230 miles per second. As a fraction of light speed, that's only about 0.0012 c, just over 0.1%. Even at that tiny fraction, the temperature difference between the hot and cold directions is about 3.4 millikelvin, a few thousandths of a degree on top of the 2.725 Kelvin baseline. So at less than 1% of light speed, your motion is already etched into the sky as a hotter, colder pattern. Instruments can read that like a speedometer. Your starship blasting along at 0.99 c would take that same effect and crank it up until the whole universe's afterglow is actively slamming into your bow. Now put your ship into that environment at 99% of light speed. From your frame, you're ploughing through the CMB. Microwaves in front of you are not just coming at you, they're getting Doppler blue shifted, just like starlight. The factor, as before, is around 14 in frequency for radiation exactly ahead of you at 0.99 c. Take the CMB's peak wavelength, about 1.9 millimeters, divide by 14, and you get roughly 0.14 millimeters, or 140 micrometers. That is no longer in the microwave band, that's far infrared, edging towards shorter wavelengths. If you push your speed a bit higher, or look at directions slightly off your exact velocity vector, parts of that forward spectrum can creep into the near-infrared or even into the visible and ultraviolet range. Remember, this is not one star or one galaxy, this is every direction in front of you. Every patch of sky contributing blue-shifted background photons. What used to be a calm 2.7 Kelvin microwave bath, almost harmless, becomes, ahead of you, a warmer, higher frequency field. It starts to behave more like a lukewarm fog of infrared light constantly hitting your ship. And if 0.99 c can do that, the next natural question is, what happens if you push gamma into the hundreds or thousands? At gamma around 1000, which corresponds to a speed so close to light that the difference is measured in parts per million, the Doppler factor for head-on radiation can be enormous. Think in terms of frequency. The CMB today peaks at about 160 gigahertz, 160 billion cycles per second. Multiply that by 1,000 and you get 160 terahertz, 160 trillion cycles per second, which is in the near-infrared, getting close to visible red light. Multiply by another 1,000 and you reach 160 petahertz deep into the ultraviolet. Push the factor higher still and you end up in the X-ray and gamma-ray bands. So at very high gamma, your forward CMB is no longer a low-energy background. A photon that started as a soft 160 GHz microwave can, in your frame, carry the energy of a UV, X-ray, or even gamma-ray photon. That means ionizing radiation, capable of knocking electrons off atoms, damaging materials and biology. Your shielding challenge at that point is no longer just protecting against sporadic cosmic rays or occasional solar storms. The entire universe's ancient afterglow, something that is normally gentle and cold, becomes part of the radiation field beating on your spacecraft. The cosmos itself is effectively trying to cook you, using nothing but its leftover Big Bang light, boosted by your own motion. This is a fundamental limit that has nothing to do with how good your engine is, or how strong your hull is. The faster you go relative to the CMB frame, the hotter and more focused this background becomes in front of you. At some point, no reasonable shielding thickness or active protection is going to keep the gamma rays and secondary particle showers to safe levels for human tissue or electronics. That sets a kind of practical ceiling on sustainable gamma, long before you get mathematically close to infinity. But there is another side to this, which is actually useful. Because the CMB fills all of space and comes from every direction, the way it looks in your sky becomes a direct measure of your velocity relative to the cosmic rest frame. You do not need road signs or external beacons, you just need to read the pattern of temperature and frequency across the sky. If the CMB looks almost perfectly uniform with tiny millikelvin ripples and no big hot-cold dipole, you are close to rest with respect to it. If one side of the sky is a little hotter and the opposite side a little cooler, like we see now from Earth, you're moving at a small fraction of light speed. As you go faster, the hot direction gets hotter, the cold direction gets colder, and the radiation becomes more and more focused into a forward cone. On a near light speed ship, you could, in principle, treat the CMB as your speedometer. The more the sky's background glow piles up ahead of you and drains away behind, the closer your velocity is to light speed relative to that cosmic frame. No human-made system can fake or override that, because it is baked into the structure of the universe itself. Astronomers already do the reverse of this. By precisely measuring the tiny dipole distortion in the CMB, they infer the solar system's speed and direction of motion through the cosmic rest frame. They are, in effect, reading our current license plate velocity just from how the background temperature varies by a few thousandths of a degree across the sky. So at relativistic speeds, the universe itself stops being just scenery. It becomes your navigation grid, your radiation source, and your speed indicator all at once. Up to now, we have talked about how near light speed changes what you see and what hits you. Colours shifting, skies collapsing forward, time outside racing ahead. But underneath all of that, there is a deeper structure controlling what you can even touch, who you can send a signal to, and which parts of the universe are forever out of reach. That structure is set by light cones, the hard geometric limits on cause and effect in spacetime. And once you start moving close to light speed, even your personal light cone, your own reachable region of the universe, begins to tilt and narrow in ways that are not obvious from just looking out a window. To understand how chasing the speed of light actually changes which parts of the cosmos can ever matter to you, you have to step back from colours and radiation and look straight at the causal map of space-time itself. How far does your influence really reach, even if you had infinite fuel and an endless life? Not in terms of how far you can physically fly, but in terms of which parts of the universe you can ever touch or get a signal from. The answer is not everywhere. and the reason is the speed of light drawing hard boundaries in space-time. In relativity, every event, every point in space at a particular time, sits at the tip of a structure called a light cone. Picture a point that's here and now for ye. From that point, light can spread out into the future in all directions at 300,000 kilometers per second, about 186,000 miles per second. If you plot that in a space-time diagram, that set of possible light paths forms a cone opening upward, your future light cone. Go the other way in time. All the light that could ever have reached you by now had to start somewhere inside another cone, opening downward in time, your past light cone. Everything inside that past cone is allowed to have influenced you by sending signals that eventually reached you. Anything outside both cones is not just far away, it's causally disconnected. Events there cannot have affected you yet, because light and any slower signal literally hasn't had time to get from there to you, and you can't affect them now because no signal you send at or below light speed can reach them in time. The speed of light is not just a number, it's the rule that decides who can talk to who and when. So even before you start moving fast, you're always living inside a causal bubble set by these light cones. The next question is, what happens to that bubble when you stop being at rest and start accelerating close to light speed? When you jump on your near-sea ship and fire the engines, your path through space-time bends. You are no longer following the same straight-time axis as the people who stayed home. From their point of view, you start leaning over in the space-time diagram, trading time for space. Your future light cone is still, locally, the same shape, because locally the speed of light is always the same. But what counts as your future and your elsewhere changes compared to the frame you left. In practice, that means some parts of the universe that used to be potentially reachable before you launched no longer are once you commit to a certain trajectory at near light speed. Think about distant galaxies on the opposite side of the sky from your direction of travel. If you had stayed on Earth, in principle, given enough time, you could have sent a signal toward them, and as long as the universe's expansion didn't drag them away too fast, that signal could eventually arrive. Those regions were inside your future light cone. Now lock your engines into a long near-sea burn in some other direction. Because you're using so much of your speed budget going that way, there are directions you effectively give up on. There are distant regions that from your new high-speed world line, you can no longer reach with a light speed or slower signal, even if you point your transmitter right at them and never stop sending. Your future light cone, as seen in the original frame, doesn't cover them anymore. You have traded causal reach in some directions for extreme motion in another. This isn't just about your choices, it also mixes with the large-scale behavior of the universe itself. Observations show that cosmic expansion is accelerating. On very large scales, galaxies are being carried away from each other faster and faster by the stretching of space. At some distance, that recession speed reaches light speed. Beyond that, you get a cosmic event horizon, regions of space whose light will never reach us, no matter how long we wait. They are permanently behind a boundary in space-time. From Earth's frame today, there is a shell of galaxies that we can see now, but that are heading toward this horizon. Light they emit today might reach us, but light they emit in the far future will not. They are right on the edge of our causal future. Now add your high-speed path. When you pick a direction and accelerate to near sea, you're not just changing your velocity, you're changing which parts of that cosmic map remain in your personal causal future. Some galaxies that would have stayed barely reachable if you stayed home slide outside your personal event horizon once you take that path. Others, maybe closer to your direction of travel, stay reachable or even become easier to contact. So the light speed limit doesn't just make things slow, it redraws your private map of what counts as the reachable universe. Parts of the cosmos are always falling off that map, either because expansion pushes them beyond the cosmic horizon, or because your own trajectory spends your causal budget in one direction at the cost of others. This is all still consistent though. You can't send signals where they can't go, but you also can't cheat and send them faster than light to get around the problem. And that brings us to the hard line you absolutely cannot cross without ripping causality apart. If somehow you had a drive that could push you faster than light, or a communication system that could send messages at 2C or 10C, you wouldn't just outrun radio waves, you would break the entire logic of before and after. Here's why. You already know that simultaneity is relative. Two events that happen at the same time in one frame can happen in different orders in another. If you now add faster than light signals on top of that, you can string together a path where, in some frame, the signal arrives before it was sent. In one frame, you send a superluminal message from A to B. In another frame, because A and B are moving relative to each other, the order of send and receive can flip. Then you let B send a reply also faster than light back to A. With the right geometry, A can receive that reply before it sent the original message, in its own frame. You've built a closed causal loop where cause and effect circle back on themselves. That's the core reason why basically every serious physical theory we have, from special relativity to general relativity to quantum field theory, locks in light speed as the ultimate limit. Once you allow faster than light signals, you lose any consistent way to say what the history of the universe actually is. Did you send the message or not? Did the event happen or not? The answer would depend on which frame you picked. At 0.99c, the universe looks warped and extreme, but the rulebook still holds. No closed causal loops, no messages from your own future, no paradoxes. As soon as you push past C, that structure collapses. So the light cone picture is not an abstract diagram, it is your actual cage. It tells you which regions of space-time you can ever influence, and which regions can ever influence you. Near light speed, your path through that cage gets weird, and your reachable patch of the universe tilts and narrows in non-intuitive ways, but the walls are always there. Up to now, we've treated space-time as basically flat. Your ship flies in a straight or gently curving line, and gravity is a background detail. But the universe has places where space-time itself is bent so hard that even light can't climb out. Near a black hole, you get all the special relativity effects we've talked about, stacked on top of extreme gravity and event horizons. What happens when you bring your near light speed ship into that environment, where light cones tip over, time slows, and orbits demand a huge fraction of light speed just to stay up? To answer that, you have to put your mental model of light cones and speed limits right next to one of the most extreme objects in the universe, and see how they team up to twist your view of reality even further. What happens when you take all the near light speed effects we've talked about, and then drop yourself next to something that already bends space-time to the breaking point? That's what you get near a black hole, where special relativity and general relativity stack on top of each other and stop being optional details. Up to now, you've been in flat space-time where gravity was basically a background annoyance. Special relativity handled everything: time dilation from your speed, length contraction along your path, Doppler, shifts, aberration, all in a clean straight grid. A black hole throws that grid away. Now space-time is curved, and gravity itself slows time and shifts light. Take a non-spinning black hole first. It has a characteristic size called the Schwarzschild radius. You can think of it as the distance from the center where the escape speed reaches the speed of light. For a black hole with the mass of the Sun, that radius is about 3 kilometers, around 2 miles. For a 10 solar mass black hole, it's about 30 kilometers, roughly 19 miles. Outside that, matter can orbit. But there is an inner limit to how close you can have a stable circular orbit. That's the innermost stable circular orbit, the ISCO, at about 3 times the Schwarzschild radius for a non-spinning hole. At that radius, orbital speeds are around half the speed of light, about 0.5 c. You're doing roughly 150,000 kilometers per second, about 93,000 miles per second, just to keep from falling in. Around a spinning or Kerr black hole, frame dragging lets stable orbits sit even closer. For a rapidly spinning hole, the ISCO can move inward to almost the event horizon itself. Orbital speeds there can reach 0.7 c or more, so gravity is giving you near light speed motion for free, in the sense that you're not burning rocket fuel to get that funds. Spacetime geometry is forcing you to move that fast if you want to stay in orbit. So near a black hole, special relativistic time dilation from your speed is already huge. On top of that, general relativity adds gravitational time dilation. Clocks deep in the potential well run slower than clocks far away, even if they are not moving. The two effects multiply. To a distant observer, your time near the ISCO crawls. Minutes for you can be hours, days, or more for them, depending on how deep you are. If time is being hammered that hard, light is going to show it. So the next question is, what happens to the photons you and the disk around you are sending out when they have to climb out of that gravity well while you're moving at a big chunk of light speed? From far away, light that leaves the region near the black hole has to fight gravity to escape. As it climbs out, it loses energy. Losing energy for a photon means its frequency drops and its wavelength gets longer, so it gets redder. That's gravitational redshift. Even if the emitter is sitting still in a local sense, a distant observer sees its light shifted to lower energies. Now put yourself in a fast orbit near the ISCO. You're moving at say 0.5 C or more, and you fire a photon from your ship, or you look at light from the accretion disk. Locally in your frame you have Doppler effects from your own motion. Light you emit forward is blue shifted, backward is red shifted, exactly like we discussed before. But when a distant observer looks at that same light, they see the combination of both effects. Photons from parts of your orbit that are moving toward them are Doppler blue shifted but also gravitationally red shifted. Photons from parts moving away are even more red shifted. The result is that sharp spectral features like the iron K-alpha line at about 6.4 kilo electron volts get smeared out, stretched and skewed. Instead of a neat spike in the X-ray spectrum, they see a broad asymmetric bump with a long red tail. X-ray observatories actually measure this. When they look at accretion disks around black holes, both stellar mass ones and supermassive ones in galactic centers, they see iron lines that are broadened and distorted exactly the way you expect from a combination of high orbital speeds and intense gravity. Those lines are direct fingerprints of special relativity and general relativity working together. So orbits at 0.3 C, 0.5 C, 0.6 C near black holes are not science fiction travel speeds. They're standard solutions to Einstein's equations. When we simulate disks around, say, a 10 solar mass black hole, the inner regions naturally settle into orbits of tens of thousands of kilometers, tens of miles per second, no, tens of percent of light speed. For a stellar mass hole, material can circle in milliseconds. For a supermassive black hole of 1 billion solar masses, inner orbits can have periods of hours or days, still with speeds at a hefty fraction of c. These inner disk zones are nature's own near light speed laboratories. Gravity is doing the acceleration and the confinement for you. Plasma flows along curved space-time, hits those high speeds, and emits light that carries the imprint of both its motion and the warped geometry around it. All of that is in the spectra and timing. But if you were actually sitting in a ship near the ISCO, what does the universe look like out your windows? From that orbit, the black hole would dominate your scio. The shadow region where no light from behind can get to you because it falls into the hole instead would cover a huge angular size. Around that shadow there would be a bright, warped ring of light from the accretion disk, bent by gravity. Light from the side of the disk behind the black hole would get lensed over the top and around the sides, so you would see the backside of the disk as a glowing ring encircling the dark center. Light paths are so curved that photons from behind you can loop around the hole and arrive from in front of you. There are multiple possible paths for light from a single source to reach you, so you see duplicate, ghost images of stars and disk features at different positions. The clear separation between in front of me and behind me breaks down. Now combine that with your own orbital motion at say 0.5 c, relativistic aberration still applies. Light from the direction of your motion is dragged forward. Light from behind gets smeared around. Parts of the disk you are moving toward look brighter and more bunched up due to beaming and aberration. Parts you are moving away from look dimmer and stretched. The whole scene is constantly shifting as you orbit, with features swinging around your field of view in ways that don't match simple circular motion. Up and down also become slippery. Gravity bends the paths of photons coming from above and below the disk plane. You can look up and see parts of the disk that are actually below you. Their light bent up over the black hole. The sky is no longer a clean dome. It's a warped, layered mess where directions are defined more by geodesics and math than by your everyday intuition. So near a black hole, at nearly light speed, you get the full tag team, special relativity from your enormous orbital velocity, general relativity from the curved spacetime, and both of them acting directly on what you see and how your time flows. It's one of the most extreme versions of what does the universe look like near light speed that physics actually lets you set up. Out in the wider universe though, you don't need to build a ship and dive toward a black hole to see matter doing this kind of thing. The cosmos is already launching entire rivers of plasma at 0.9 C, 0.99 C, and even faster in the form of jets from active galactic nuclei and gamma-ray bursts. Those jets are as close as we get to real physical near-light-speed starships, and they show us in brutal detail what happens when whole chunks of matter and radiation spend their lives moving just shy of light speed. Near light speed travel sounds like pure theory until you realise the universe is already doing it, not with tiny particles in labs, but with whole rivers of plasma launched from galaxies. These flows are moving at speeds your starship concepts barely touch, and they show in real data what matter looks like when it lives at 0.9 C and beyond. Active galactic nuclei, or AGN, sit in the centres of galaxies where a supermassive black hole, millions to billions of times the sun's mass, is feeding. Gas spirals in, forms a hot accretion disk, and magnetic fields twist that inflowing plasma into narrow jets, shooting out from the poles. Those jets can extend hundreds of thousands of light years, longer than the entire galaxy that launched them. Astronomers track bright knots in these jets using very long baseline interferometry, which links radio telescopes across continents to get insane resolution. By watching how these blobs shift on the sky over years, they can infer their actual velocities. The numbers come back in the range of 0.9 to 0.99 times the speed of light. That means gamma factors of a few up to 10 or more, not for single protons, but for macroscopic clumps of plasma. So out there, far away, nature has already built vehicles moving at the speeds you've been talking about for a hypothetical starship. Entire chunks of magnetized gas are spending millions of years at these velocities, not for a few laps around a collider ring, but across intergalactic distances. Once you track those blobs, something weird pops out. In some jets, they seem to move faster than light across the sky. Measurements show components that, based on their angular motion and distance, appear to be moving at several times c. That would break everything you've heard about speed limits if it were real motion. It isn't. It's relativity playing a geometry trick. Here's what's going on. You have a jet moving at, say, 0.99 c at a small angle to our line of sight, not straight at us, but not far off. When a bright knot in the jet moves from one point to another, you see it at the first position, then you see it at the second, slightly closer to you along the line of sight. Light from the second position has less extra distance to travel than you'd naively expect, because the knot has moved partly toward you while its light is on the way. So the time between we see it here and we see it there is shorter than it would be for an object moving sideways. When you divide the apparent distance across the sky by that shortened time, you get an apparent speed that can exceed c. But the true 3D velocity of the blob through space never crosses light speed. It stays at 0.9 c, 0.99 c, something like that. The superluminal part is just a projection effect plus the finite travel time of light. That's a case where relativity itself creates the illusion of breaking its own rules while still obeying them exactly. The jets look like they're cheating light speed, but they're not. GN jets are long-lived, steadish systems. There is another class of event where the universe fires a near light-speed jet in one brutal burst, spends it in a matter of seconds, and then goes dark. Those are gamma-ray bursts, GRBs, the most violent explosions we've ever seen. A single long GRB can release in 10 or 20 seconds as much energy in gamma rays as the Sun will radiate in all forms over its entire 10 billion year life. The leading models involve very narrow ultra-relativistic jets, with gamma factors around 100 or even higher, launched during the collapse of a massive star or the merger of compact objects like neutron stars. At gamma around 100, your time dilation and beaming effects are extreme. From the jet's frame, external time is crushed, and almost all the radiation and matter is packed into a tight forward cone. To any hypothetical observer carried along inside such a jet, the outside universe would be violently anisotropic, insanely lopsided. Ahead, the CMB and any starlight would be catastrophically blue-shifted into high-energy X-rays and gamma rays, exactly the kind of photons we detect from GRBs. These jets are not stable transports. They're more like single-use near-light-speed cannons. They form, fire, dump a ridiculous amount of energy into a narrow solid angle, and then slow down and fade as they interact with surrounding gas. But during that brief window, they are exactly what you've been talking about. Big chunks of matter and radiation living at Lorentz factors of around 100, telling you how space-time behaves when you really lean on it. The natural question is, what would it actually be like inside one of these high gamma jets, from a local observer's point of view? Inside such a jet, your universe would not feel symmetric. Most of the energy, particles, and radiation would come from a narrow forward angle. Because of beaming, the jet's own emission is focused along its axis. Because of Doppler and aberration, external backgrounds are also squeezed into that same region. The rest of the sky, sideways and backward, would be relatively empty and cold. Structures you pass, like gas clouds or surrounding material, would evolve in extreme time-lapse. In the external frame, the jet might take thousands of years to cross a region. In the jet's frame, at gamma 100, that whole crossing could correspond to only tens of years of proper time. Features in the environment compress into a shorter narrative, density jumps and shocks piling into your history faster than they do for a slow observer. The conditions are so harsh that no normal matter inside the jet is going to be macroscopic, organised stuff like a spaceship. You're dealing with hot plasma and high-energy particles. But conceptually, it's the same question you're asking. What does reality look like when your velocity is that extreme? GRBS and AGN jets answer by acting it out for real and letting our telescopes pick up the light. By studying their spectra, light curves, and apparent motions, astronomers back out the speeds, the gamma factors, the beaming angles, and even the structure of the surrounding medium. Whose models match observations, they confirm that special relativity's rules about time dilation, Doppler shifts, and aberration hold, even in the most violent environments we can see. So the universe at near light speed is not just a thought experiment you run on a whiteboard. The cosmos has already deployed giant natural test vehicles, firing plasma at 0.99 C, running gamma around 100, and smashing that matter into whatever lies in its way. We are catching the flash, reading the imprint, and seeing that the same equations work across 20 orders of magnitude in energy. But jets and disks are still bulk flows of many particles at once. If you want to know how individual particles behave when you push them to the edge, down to the level where a single proton carries more kinetic energy than a fast-pitched baseball, you have to look at something even more extreme. Space is constantly bombarding Earth with those particles. They're called cosmic rays, and at the highest energies they are nature's almost light-speed bullets, testing relativity at gammas so huge the decimal expansion of their speed is almost all nines. To see just how far the universe has already pushed matter toward the ultimate speed limit, and what that means for your dream of a relativistic starship, you need to look at these ultra-high energy cosmic rays and the giant detectors we've built to catch them. Space is not empty or calm. It is constantly firing high-energy particles straight through you and through Earth's atmosphere. These are cosmic rays, and at the top end they carry so much energy that a single proton can hit with the punch of a thrown baseball. That is how far nature has already pushed matter toward the speed of light. Cosmic rays cover a huge range of energies. The low-energy ones are common and mostly harmless. They come from the sun and from ordinary processes in the galaxy. As you go up in energy, they get rarer but far more interesting. The most extreme events we've measured reach around 10 to the 20 electron volts. Convert that and you get about 8 joules carried by one proton or one atomic nucleus. 8 joules is roughly the kinetic energy of a fast baseball, but here it's squeezed into a single subatomic particle. To carry that much energy, the particle's speed has to be insanely close to light speed. Writing it out looks ridiculous. You get numbers like 0.9999999999999999995 times the speed of light depending on the exact energy in the particle's mass. The difference between its speed and c is so small that for many purposes, you can treat it as moving at c, but relativity still insists that its gamma is enormous. We're talking gamma factors of 10 million, 100 million and beyond. So when you imagine an ultimate near-light-speed starship, remember this. Space is already throwing particles at Earth that are much closer to C than any bulk object we could realistically launch. These are nature's test shots, constantly checking whether space-time really behaves the way special relativity says it should, even at absurd energies. When these cosmic rays hit the upper atmosphere, they don't just stop, they slam into nuclei in the air and create cascades of secondary particles called air showers. Among those secondaries are muons, the same unstable particles we talked about earlier. At rest, a muon lives on average 2.2 microseconds before decaying. That lifetime would only let it travel a few hundred meters even if it were moving at light speed. But the muons produced by high-energy cosmic rays are moving at well over 0.98 C, often much faster. From our frame, their internal clocks are slowed by time dilation. Their gamma might be 10, 20, 100 or more. Multiply their rest lifetime by that factor, and suddenly they have enough time in our coordinates to travel tens of kilometers, even hundreds before they decay. Detectors on the ground and on mountaintops see large numbers of these muons. The vertical distribution, how many reach at different depths, matches the predictions that include a relativistic time dilation. If you tried to model the showers with classical non-relativistic lifetimes, the flux at the surface would be far too low. The actual data only makes sense if spacetime is stretching the muon's proper time exactly the way special relativity says. To study the highest energy events, you can't just put a small detector somewhere and wait. The air showers from ultra-high energy cosmic rays can spread over many square kilometers. That's where observatories like the Pierre Auger Observatory in Argentina come in. Auger spreads an array of water-Cherenkov detectors over about 3,000 square kilometers, roughly 1,200 square miles. Each station is a tank of purified water with light sensors. When charged particles from an air shower pass through, they move faster than light travels in water, and they emit a flash of Cherenkov light, a kind of optical shockwave. By recording which tanks light up, how bright the flashes are, and when they arrive, researchers reconstruct the geometry of each shower. From that, they can infer the direction the original cosmic ray came from and its energy. The timing patterns only fit if you assume the shower particles are moving at nearly light speed, with relativistic time dilation controlling their decay and interaction lengths. The energies Auger and similar experiments measure, often in the 10 to the 18 to 10 to the 20 electron volt range, point back to extreme astrophysical accelerators, like supernova shock fronts, active galactic nuclei, or highly magnetized neutron stars called magnetars. Whatever the detailed mechanism, the result is clear. The universe is routinely pushing particles to gamma factors that dwarf anything we can do in the Large Hadron Collider. The LHC reaches proton energies up to a few times 10 to the 12th electron volts per particle. Ultra-high energy cosmic rays can be 1,000,000 times more energetic, or more, yet even at those energies, when we look at how showers develop, how muons survive, how arrival times stack up, everything lines up with the same old special relativity. Time dilation, length contraction, the speed limit, all are still in force. There is one more twist though that shows how these particles don't just confirm the rules, They also stress test them and our understanding of the universe on very large scales. That twist is the Greisen-Zatsepin-Kuzmin limit, or GZK limit. The idea is this: at extremely high energies, a proton or nucleus flying through intergalactic space isn't just moving through emptiness, it is moving through the cosmic microwave background photons. From the proton's frame, those low-energy microwaves are blue-shifted into higher-energy photons. If the proton's energy is too high, collisions between it and these background photons become inelastic, meaning the proton can lose a big chunk of its energy, for example by producing pions. That sets up an effective cutoff. Over long distances, cosmic rays above a certain energy, around a few times 10 to the 19 electron volts, should lose energy and be degraded. We shouldn't see many particles above that arriving from far away, because they'd get sandpapered down by the CMB before reaching us. But we do detect events right up near that limit. They're rare, but they're there. That raises questions. Are their sources relatively nearby, so they haven't had time to lose much energy? Are magnetic fields and paths more complicated than we think, letting them arrive with higher apparent energies? Does our modelling of the backgrounds need tuning? In other words, ultra-high energy cosmic rays are not just rubber stamping special relativity, they are also probing how that relativity interacts with cosmology, background radiation, and large-scale structure. They show that the basic spacetime rules still hold, but they also push us to refine where those rules meet the messy details of the real universe. So when you think about building a starship to chase the speed of light, remember you are stepping into a game the universe has been playing for billions of years. It has already fired particles at gamma 10 million, already used the CMB as a friction field, already shown that even at these extremes, the light speed limit and time dilation rule everything. That leaves one big, brutal question. Even if the physics lets you get arbitrarily close to light speed in principle, what does it cost in practice? How much energy do you need? How dangerous is the environment? What does it do to human bodies? To answer that, you have to stop watching nature's accelerators and start doing the accounting for your own, and the numbers you get for an almost light-speed starship are not friendly. To see why a near light-speed starship is so odd, you have to look at the energy bill, not the cool concept art. The physics lets you approach light speed, but the price tag explodes long before you get there. Start simple. In everyday life, kinetic energy grows like 1/2 times mass times speed squared. Double your speed, you quadruple your energy, still manageable. Near light speed, that rule breaks. You have to use the relativistic version, where kinetic energy is the Lorentz factor gamma -1, multiplied by the mass and by the speed of light squared. Take a starship mass of 1 million kilograms, that's 1,000 tons, about the mass of a large ocean ship or a big skyscraper's steel frame. Choose a cruise speed of 0.99 c, 99% of light speed. At that speed, gamma is about 7.1, so gamma -1 is about 6.1. Multiply 6.1 by 1 million kilograms, and then by the square of the speed of light, and you get roughly 5.5 times 10 to the 23 joules of kinetic energy. Now compare that to humanity's total annual energy use, all power plants, all cars, all planes, everything. That's around 6 times 10 to the 20 joules per year. Your single 1,000-ton starship at 0.99 c needs almost 1,000 years of current human energy production just to accelerate one way, ignoring inefficiencies. Ignoring the fact that rockets always waste energy throwing propellant backwards, and ignoring that you also have to slow down at the end. So approaching light speed in engineering terms means accepting energy budgets that make entire civilizations look small. And that's before you talk about where that energy actually comes from. Chemical rockets are instantly out. They convert only a tiny fraction of mass to energy. Nuclear fission is better, but still only taps about 1% of the mass energy of the fuel. Fusion, the process that powers the sun, can convert on the order of 0.7% of the mass of hydrogen into energy when you fuse it all the way to helium. In metric terms, 1 kilogram of fuel gives you about 6 times 10 to the 14th joules if you could capture everything, which you can't. Antimatter annihilation is the theoretical king, because it can, in principle, convert 100% of the combined mass of matter and antimatter into energy. 1 kilogram of antimatter plus 1 kilogram of normal matter would give around 1.8 times 10 to the 17 joules. That's huge, but we can barely make nanograms of antimatter today, and storing even micrograms safely is a nightmare. Magnetic traps, perfect vacuums, zero contact with normal material, constant power to keep it confined. Any failure is an instant multi-kiloton explosion. Because carrying that much fuel is a problem, people look at external propulsion, like beamed sails. In that idea, you put a very light, very reflective sail, maybe grams to kilograms in mass, and you hit it with a giant laser or microwave beam from your home system. You don't carry your propellant, you ride a push from behind. In metric terms, huge laser arrays on the order of gigawatts or terawatts push a tiny sail to a fraction of light speed, maybe 0.1 c or 0.2 c. In imperial terms, you're talking about power stations orders of magnitude larger than anything we've built, just to push something the mass of a small car. Even if you get that working interstellar dust and the blue shifted backgrounds we talked about kick in long before you sniff 0.9 c, past maybe 0.3 c or 0.5 c, the environment ahead of your craft stops being empty space and starts acting like a sandblaster and a radiation cannon combined. Interstellar space is not perfectly clean. There are dust grains and stray atoms everywhere, maybe a few atoms per cubic centimetre, plus occasional bigger grains the size of sand or pebbles. At 0.1 c, 10% of light speed, a grain of sand hitting your ship has the energy of a high explosive shell. At 0.9 c, the kinetic energy scales with speed squared and with gamma, so impacts become more like tiny nuclear events in terms of the local damage. One grain can vaporize a patch of hull, generate X-rays and gamma rays, and send a shockwave through your structure. Designs for relativistic craft almost always include heavy forward shields, maybe tens of centimeters or meters thick in front, made of dense material like water, ice, or special composites. Some concepts add a sacrificial dust cloud fired ahead of the ship to sweep up larger particles before you hit them. Others rely on magnetic fields to deflect charged particles, but those fields don't stop neutral dust. One way or another, the universe becomes your crash test wall, and every kilometre you cross at high speed is another chance for a catastrophic hit. Then there's you. Human bodies are not optimised to live as payloads in a constant high acceleration environment. You can handle a few G for short periods, in fighter jets or during rocket launch, but that's minutes, not years. For long-term comfort, you want to stay around 1 G, about 9.8 meters per second squared, roughly 32 feet per second squared. That's what you already live in thanks to Earth's gravity. If your starship accelerates at 1 G in deep space, pointed nose up, you feel normal gravity toward the back of the ship. From your perspective, you're standing on the deck, feet on the floor, with a constant downwards pull that feels like Earth. The bonus is, at 1 G you reach 0.9 C in a bit under a year of onboard time. Half that time you accelerate, half you decelerate, flipping the ship around in the middle. Proper relativistic math gives the exact numbers, but the rough scale is months, not centuries. The problem is sustaining that. Your bones, heart, circulatory system and inner ear can live with 1 G because they evolved in it. But any higher constant acceleration, say 2G or 3G, quickly becomes stressful. Blood pools differently, your heart has to work harder to push blood to your brain, your spine is under extra load. Fighter pilots can survive 9G for a few seconds with special suits and training, not for months in a row. So a realistic high-speed mission has to juggle many constraints at once. You want high acceleration to reach a useful cruise speed before you die of old age. You need enough propulsion power to supply that acceleration for months. You need huge radiation and impact shielding to survive the environment at that speed. And you need to keep the acceleration low enough, around 1 G or less, that humans can function, sleep, work, and not suffer long-term damage. That makes the whole project as much a bioengineering and psychology problem as a physics one. You're not just building a rocket, you're building an artificial world that keeps people mentally stable and physically healthy, while the outside universe is trying to shred your hull and fry your electronics. Put all this together and you get a clear picture. Near light speed is not impossible according to the equations, but it is brutally expensive in energy, dangerous in terms of impacts and radiation, and punishing for biological passengers. You can get arbitrarily close to C on paper, but every extra 9 in that decimal demands more energy, more shielding, more sacrifice. And here's the key tension. For you with mass, the closer you get to light speed, the more the universe pushes back. For light itself, none of this applies. A photon doesn't pay an energy penalty to speed up. It is born at light speed and stays there. It doesn't feel time stretching, it doesn't feel acceleration, it doesn't experience a journey the way you do at all. So the next question is the deepest one in this whole story. If you spend all this effort and never quite reach C, what is different about light that lets it live at that limit for free? And what does that say about space and time themselves? When, from the photon's point of view, distance and duration basically vanish? To answer that, you have to stop thinking like an engineer and look straight at what relativity says about proper time along a path that moves at light speed, and why, for a photon, there is no trip between emission and absorption at all. How can a photon leave a galaxy 10 billion light years away, cross the universe for 10 billion years in our coordinates, and yet, in a strict relativistic sense, not experience any time at all between departure and arrival? That sounds like a word game, but it just drops straight out of how space-time is built. In relativity, every object traces out a path through space-time, called a world line. Along that world line there is a special clock, the one moving with the object. The time that this clock measures between two events on that path is the proper time. For you, walking across a room, the proper time between start walking and stop walking is just how many seconds your wristwatch ticks. For an astronaut orbiting Earth, the proper time is what their onboard clock reads between launch and landing. For any object with mass, that proper time between two distinct events is always positive. No matter what route you take through space-time, as long as you don't move at light speed, your personal clock always accumulates some amount of time. It might be less than someone else's, because of time dilation, but it's never zero between genuinely separate events. Light is different. In relativity, you can classify separations between events as time-like, space-like, or light-like, depending on how they relate to the speed of light. For a light-like separation, the path between the two events is exactly the kind of path light can follow. Along that type of path, the space-time interval, the thing that for massive objects turns into proper time, is exactly zero. Not small, not just reduced, but mathematically zero. So for a photon travelling along a light-like path from one emission event to one absorption event, the total proper time along its world line is zero. There is no way to place a clock on the photon and have it tick forward, because the amount of time between those 2 points, in the photon's own sense, is not a small positive number, it is identically zero. That leads straight to the next question. If the proper time is zero, is it meaningful to talk about what light experiences on its journey at all? Here you have to be very careful. Light has no rest frame. There is no valid way inside special relativity to jump into a coordinate system where a photon is at rest and everything else is moving. All the frame changes you're allowed to do keep the speed of light the same number. To make the photon stand still, you'd need a transformation that breaks the theory. So the perspective of light is not a real reference frame, it's just a phrase people use loosely. But you can still use the math as a guide. Take a photon emitted by a star 10 billion light years away. In the rest frame of the galaxy, and in our cosmological frame, that photon was emitted 10 billion years ago, travelled across expanding space, and gets absorbed by an atom in your eye or a sensor in a telescope today. During that 10 billion years, galaxies formed and merged, stars were born and died, planets cooled, life evolved. There is a huge before and after story for the universe between those events. Along the photon's light-like path though, The proper time between emitted and absorbed is 0. If you use that as a stand-in for what the photon itself experiences, then there is no between at all. There is no stretch of time with intermediate moments. There is just emission and absorption, connected by a null interval. The universe can evolve for billions of years while that photon is en route in our frame. But for the photon, in this strict sense, there is no passage of time between those endpoints. The same holds for every photon, whether it's crossing a room in a nanosecond, bouncing inside a fibre optic cable, or travelling from the early universe to a radio dish. Proper time along the light-like world line is always 0, so if you try to imagine that photon watching scenery go by, seeing stars redshift, watching galaxies drift, you are forcing human, slow, massive intuition onto an object whose clock never ticks at all. That leads to a hard conclusion. In a deep technical sense, the universe at the speed of light does not look like anything, because there is no sequence of experiences to build a view from. There is no flow of time, no aging, no changing perspective along a photon's path. You can talk about what different massive observers see as they approach light speed. You can talk about how signals propagate at light speed. But for light itself, there is no internal slideshow of the journey. There is just a null path sewn into space-time, with no proper time distance between the start and the end. So when you ask, what does the universe look like at the speed of light? The strict answer is, for an actual photon, that question has no content. There is no valid rest frame, there is no proper time, there are no intermediate snapshots. Instead, all the interesting, distorted views we've been talking about belong to observers who stay below light speed, who still accumulate some proper time, and who can therefore have a series of experiences. Some physicists and philosophers look at this and push it one step further. They notice that in many regimes, the laws of physics don't single out a special now. The equations often treat past and future symmetrically. Combine that with the idea that light's world lines have no flow of time along them, and you get the suggestion that maybe the universe is best thought of as a four-dimensional block, where past, present and future all exist together. In that view, now is not a universal slice everyone shares, it's just the particular cut-through space-time associated with your current motion and position. You don't have to fully adopt that block universe idea to follow the physics. You can treat it as one interpretation among several. But chasing the question of what reality looks like at light speed pushes you right up against this edge where the familiar idea of time as a flowing river, the same for everyone, no longer works. Light doesn't experience a river at all, it just connects two shores with no time in between. For you, with mass, you never quite reach that limit. You always move on time-like paths, you always accumulate some proper time, you always get a sequence of moments, but as you push your speed closer to C, your personal river of time slows down compared to the cosmos. Distances shrink, skies warp, and your slice of now tilts. Everything you call reality bends around that one constant, the speed of light. So the final step is to accept what all of this really means for you. Space and time are not separate, fixed backgrounds. They are part of one structure, space-time, and your motion through it rewrites your private map of distances, durations, and even the present itself. The last thing to sort out is what that does to your idea of reality as a whole. Once you accept that there is no single universal now, no one true picture of the universe, and that the light speed limit isn't just a curse, it's the thing that keeps any of this from collapsing into paradox. By this point, you've watched almost every normal thing you believe about reality fail. Space can shrink, time can slow, colours can jump from safe visible light to lethal X-rays, the whole sky can collapse into a blazing tunnel ahead of you, and light cones quietly decide what can ever talk to what. The conclusion staring you in the face is blunt. Space and time are not two separate arenas. They are coordinates on one object. Space-time and the speed of light is the fixed conversion rate between meters and seconds. In normal life, you treat distance and duration as different kinds of stuff. A meter is not a second. A kilometer is not an hour. Near light speed, that split falls apart. Change how fast you move, and meters turn into seconds and back again, through that one constant, about 300,000 kilometers per second, roughly 186,000 miles per second. Your speed decides how much of what you used to call space moves into your time budget, and how much of your time turns into effective distance. Length contraction is that in action. At 0.99 c, the 4.3 light years to Alpha Centauri in the galaxy frame become about 0.6 light years for you. Time dilation is the flip side. Those 4.4 years on Earth become 7 or 8 months on your ship. The same space-time separation between departure and arrival gets carved up into different amounts of space and time depending on your motion. That only makes sense if space and time are just different projections of the same deeper structure. And it's not just distances and durations. Your whole map of the universe depends on how you move through that structure. There is no single God mode snapshot of what the universe looks like right now that everyone agrees on. Every observer with a different velocity takes a different slice through space-time. At low speeds, those slices almost line up, so you can pretend there's one master view. But as you push to 0.9 c, 0.99 c, 0.999 c, the differences blow up. One near light-speed traveller looks out and sees distances along their path, flattened, external clocks racing, the CMB piled up hot in front and drained behind, galaxies whizzing through centuries of evolution in months of ship time. Another traveller moving in a different direction at a different speed sees a completely different pattern, different parts of the universe moving in fast forward, different regions becoming unreachable, a different CMB dipole. Both are right, because what they are slicing is not a 3D universe that updates in one universal time, but a 4D space-time where space at an instant is a choice, tied to each observer's motion. Your velocity doesn't just change what you see, it rewrites your personal coordinate grid over the same underlying events. Once you accept that, the idea of a universal present moment disappears. The question, what is the universe doing right now at the Andromeda Galaxy, does not have a single answer. It has many answers, one for every possible state of motion you could be in when you ask. If you're sitting on Earth, you can define a now in which Andromeda is at some stage of its evolution. Certain stars have exploded, others haven't. If you're on a ship rushing toward Andromeda at 0.99 c, your plane of simultaneity tilts. In your now, Andromeda might be further along, or less evolved than Earth would say, by millions of years. If you're rushing away from it, you get a different slice again. For nearby things, like your desk or the moon, those differences are microscopic, so Newton's picture of one global time works well enough. For distant galaxies and near light-speed travel, those differences dominate. So there is no single cosmic clock everyone is reading. There is just proper time along each world line, and many different ways to label simultaneous across space. That's why the question, what does the universe look like at the speed of light, is fundamentally misaimed. At light speed, there is no proper time, no valid rest frame, no sequence of nows to build a view from. All the wild visuals you've walked through belong to observers who stay below C, each carrying their own private slicing of reality. That might make the speed of light feel like a cruel barrier, a prison wall that keeps you from ever riding a photon or sending a message instantly. But that same wall is what keeps the universe logically consistent. Because C is finite and universal, light cones exist. Because light cones exist, you can draw clean lines between what can affect what, and in what order. Cause stays before effect in every allowed process. Because nothing outruns light, you can't send a signal into your own past. You can't build closed causal loops where a message arriving too early stops itself from ever being sent. Relativity of simultaneity becomes strange, but it never produces real contradictions, because all physical influences respect those cones. If faster than light travel were possible, you could jump outside your own light cone, combine that with tilted planes of simultaneity, and design paths where, in some frame, you receive information before the event that created it. Physics would lose any stable narrative of what actually happened. Initial conditions wouldn't be well defined. Predictions would stop making sense. Science would break. Instead, the universe forces you to play by strict rules. You can go very fast, but not past c. You can slow your own proper time compared to the outside, but you can't make it run backwards. You can flatten distances and watch galaxies age in fast forward, but you can't skip behind your own timeline. That harsh limit is exactly what makes a coherent, testable, predictable universe possible. So where does that leave you? You never get to sit on a photon and watch the cosmos. There's no view from light speed that feels like your daily life, stretched. What you can do is push yourself close to that limit in thought experiments and eventually with technology, and let the equations show you how reality bends as you do it. When you accelerate towards 0.99c, you're not just going faster, you're changing how big the universe is in front of you, how fast other clocks tick, which events are in your present, which regions you can still influence, and how the background glow of the Big Bang hits your hull. You're learning the hard way that the real structure underneath your everyday world is space-time, not separate space and time, and that light speed is the conversion factor welding them together. Once you see that clearly, you don't look at the night sky the same way again. Every star, every photon, every GPS signal, every cosmic ray is quietly following those same relativistic rules, whether you're crawling at highway speeds or racing at 0.99c. The universe hasn't changed, you've just pulled back the curtain on how it was working the whole time. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.